All right. Hello, class. Mr. P here. I'm pre-recording this lesson because I will be absent on the day that I would be teaching this. You guys are going to watch this lesson. And right now is my first reminder to fill in the attendance form if you haven't already. You need to fill in the attendance form at the correct time for this class. So if you are not filling out the form correctly at the correct time, you're going to be marked as absent. I added a button to the Canvas page that says that allows you to check your attendance status. So if you check your attendance and it's still red next to your name, you need to send me a Canvas message. Otherwise, I will mark you as absent. Okay. So this is your first reminder. I'm going to have two reminders. There's going to be one at the end of the lesson as well. We've spent the first part of the semester talking about electric fields, and then we talked about magnetic fields. And so now we're going to talk about electric circuits. Okay? So here's a battery. All right, and this is a AAA battery, and I don't know if my camera will be able to focus on it. Let's see. Oh, it can. Let's see. Maybe it can't. What I'm trying to get is that number. There's a number right there. And I don't think it can focus on it. I'm going to go really close and see if it can get it. That number right there. Okay, yeah, I can't focus on it. But that number says, maybe my document camera can. Let's try that. Nope. Too small. That number says 1.5 V. So what does this mean? What does this mean? Okay. So that is the first part of this lesson. So I encourage you, if you have any batteries laying around, if it's a AA battery, or if it's a AAA battery, or if it's a C battery, or if it's a D battery, all of those are going to say 1.5 V somewhere on the side, okay? And so that is called the voltage. All right? So this really means 1.5 volts, okay? So voltage actually has two names, okay? Sometimes you can call it a voltage. So if you're going to go into electrical engineering, you're probably going to be calling it mostly voltage. Or if you're in the context of pure physics, you would probably call it electric potential difference. Now, when I started college, I was actually going to be an electrical engineering major, and a physics major, but then I decided to switch to physics and math. So, I kind of have voltage ingrained in my head because I started out as an electrical engineering major, but I'll call it both. So basically what voltage is, or electric potential difference, is it is a force, or you could think of it intuitively. So this isn't the mathematical definition. We're going to learn the mathematical definition in a second. But intuitively, it's a force that causes current to flow. So voltage is the thing that makes electric current flow. All right?
What you do, Hazel?
So, and that's intuitive. Okay, so don't, that's not the strict definition of what it is, but it's intuitive. And so if you think about it, 1.5 volts, all right, that's measuring how much force there is to make current flow. Okay. Now, what's the difference between a AA battery and a AAA battery and a C battery and a D battery? Those are all 1.5 volt batteries. The difference is in terms of capacity, because what's happening when the battery is forcing electric current to flow, a chemical reaction is happening inside the battery. And once there are no more reactants left inside this battery, it can't force the current to flow anymore. Okay? So you've used up the ability to make current flow. So the bigger the battery is, the more reactants it has inside, and it can force the current to flow for a greater amount of time. So it has nothing to do with the force. It has everything to do with the amount of endurance the battery has. So bigger batteries are going to have more endurance and be able to last longer while forcing the current to flow. Okay. So, yeah. If you think about an outlet also has a voltage in your house that's 110 volts. Okay. Some of you have okay, so double A, I'll write them all down. Double A, triple A, C battery, D battery. Those are all going to be 1.5 volts. Okay. Things like a lantern battery. You can get a lantern battery. Those tend to be 9 volts. You can also get just 9-volt batteries. Okay. Car batteries are, I believe they're 12 volts. Don't quote me on that, but I believe they're 12 volts. Your power outlet, 110 volts. Okay. And if you have some kind of an industrial, like a lot of times garages will actually have 220 volts, 220 volt outlets, because in the garage you might have tools and things that really need a lot of force. Okay, so you like welders are usually going to want 220 volts. Things like table saws, 220 volts. So big industrial type equipment is going to use more voltage, have specialized outlet. Okay, so what is the mathematical definition of potential difference? Okay. So the mathematical definition, okay, let's say you have an electric charge Q, okay, and it starts out here, and it has an initial potential energy here, okay, and then it moves someplace else, okay, and it ends up with a final potential energy, all right? Then the potential difference is denoted by delta V, and it is equal to U final minus U initial. So the difference in potential energy divided by the amount of charge that moved. Okay? So that is how it works. Now, if we think about an electric circuit, let's suppose I have an electric circuit. So here's my AA battery, for example. All right. You guys know that this is the positive terminal of the AA battery. If you don't, you do now. And here's the negative terminal. And then let's say you take a wire and you hook it up. Okay. When the charge comes out of the positive terminal, it has a high potential energy. Okay. And then it goes around the circuit and it comes back to right here. And when it arrives at the negative terminal of the battery, it has some final amount of potential energy, which is low. Okay. And so what happens is the battery charge will flow. So charge will flow. So charge / current will flow from high to low potential. So what that means is that delta V is going to be less than 0. Okay? So what happens is the current flows out the positive terminal of the battery, the potential drops, electric potential drops, or the voltage drops, if you will, as it goes. And then the battery builds the potential back up again, and then the cycle repeats. And so it just keeps going around and around and around. Okay? So that is electric potential difference, also known as voltage. So now we're going to have a quick interlude where I wanted to talk about insulators versus conductors. So if we think about any material, the atoms are in some regular pattern. So here are the atoms, okay? So these are supposed to represent nuclei. You guys know that the nucleus of an atom is positively charged. And then around each nucleus is there's an electron cloud. Okay, so this is the electron cloud. If you have an insulator, the electrons are stuck to a single nucleus. Okay? Now, because the electrons are stuck, there's going to be no current. Because if you recall, current is the flow of electric charge. So if the electrons can't move around, they're stuck. You can't have any current flow. So how does this differ from a conductor? Well, a conductor, you still have the nuclei in a regular pattern like this, but conductors are materials where the electrons are not stuck. Well, I shouldn't say all of the electrons are unstuck, but at least some of the electrons from each atom are free to roam around the entire material, okay? So we have, maybe we have 1 or 2 electrons that are still stuck, but then the other 7 are just YOLOing it through the material. 1, 2, 3, 4, 5, 6, 7. So they can just roam around wherever they want to go to their heart's content. Okay? Sometimes they can bounce off of stuff, but they're just going wherever they want. So, doom, pew, 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 like that. They're just going wherever they want. Okay? So the electrons, some electrons are free to flow through the bulk of the material. Okay? And so that means that current can flow. All right? So what I want to think about is, what is current? So the next part of this is, what is current at the atomic level? Okay? And the important point here is that it is not the flow of positive charge. It's the flow of negative charge. It's the electrons that are moving around. Okay? This took a long time for people to figure out. Okay? This was not obvious at all that it was the electrons that were moving around. So the positive nuclei are basically like the skeleton. They're the rigid structure of a material, and the electrons can move around within that rigid structure. Okay. So the nuclei are positively charged. They're big, they're heavy, and they're rigid. They're stuck in place. The electrons are light and they're moving around. Okay. So basically, it is the flow of electrons. All right. So excuse me. Yeah. Now here's something that's interesting. All right. If the electrons themselves are flowing this way, okay, so this is the flow of electrons, then the current is actually defined as flowing in the opposite direction. So if I say the current is going towards the camera, then that means that the electrons are actually moving in the opposite direction. So this is called the conventional current flow is opposite the direction of electron flow. Okay, so that's an important point. So the current is going the opposite direction. Why is that? Because it was an accident. All right. We had defined electric current before we even knew what an electron was. Okay. So the term electricity was defined before electron. All right. So we knew about electric current before we knew about electrons, and so we were just like, well, we'll just call this the direction of current flow. And then once we figured out what the actual thing that was flowing was, and we found that it was moving in the opposite direction because it has a negative charge. Okay, so the reason that it's opposite is because current is defined in terms of the direction of positive charge flow. So in this case, negative charge flowing to the right is like positive charge flowing to the left. So that's why there's this. So we didn't know that the thing that was flowing actually had negative charge until quite a bit after we knew what electric current was. Okay. So there's another formula that IB wants you to know. So first of all, current is the rate of flow of charge. So it's dq dt. It's measured in amps. Okay. But IB has a second equation that they want you to know, okay? And this equation really shows you what current is at the atomic level, okay? And so the equation is I equals, my pen is dying here. Let me switch to this one. Q N A V. Okay. So what do all of these? So this is a description of current at the atomic level. So what is this? Q is the charge of the individual current carriers. Okay, so in the case of an electron, it would just be the charge of an electron. So right. So this would be, negative 1.6 times 10 to the minus 19 coulombs. You should put an absolute value there just to not get confused. Okay. So obviously, the more charge the individual current carriers have, the more current is going to be flowing. I hope that's obvious. N is the number of current carriers per volume. So that is basically it's the density of current carriers. So it's number per volume. So if you have more current carriers within a material, all right, then that means that when those current carriers flow, there's going to be a lot more current. All right. A is the cross-sectional area of the wire the current is flowing through. So, if usually wires have a circular cross-section. So, you have a wire that looks like this, okay? And the electrons are flowing through the wire like this, all right? And this would be the cross-sectional area. So the more area you have, the more space there is for charge to flow. It's like a pipe, right? If you have a big pipe, a lot of current can flow through it. A lot of water can flow through it. Same thing with wires and electric current. The thicker the wire is, the more room it has for charge to flow. And then lastly, the V is called the drift speed, which is basically how fast are the charge carriers moving through the wire. So because it's a rate of flow, the faster they're going, the more charge you have moving down the wire. Now, why is it called the drift speed? That is because as the electron is moving down the wire, it doesn't just go in a straight line. It's bumping into stuff. It's like so it's bumping into stuff, and as it bumps into stuff, so the electrons are actually going really fast, but they don't really make very much progress because they're bumping into stuff so often. Okay, so if you think about an electron moving down a material, it's not just like that. It's like and then it makes it to the other side. Okay, so it's the speed. So even though it's moving really, really fast, it's not making a lot of progress. And the drift speed is the speed of the progress. Okay, so it's different from the actual speed of the electrons. Um, so this is what makes up current at the atomic level. And IB wants you to know that formula. Personally, I think it's a formula that is not really appropriate for this level of physics, but IB, they know everything. They're really impressive, and they want you to know this. They think this is important, so I'm going to teach it to you. Gosh darn it. So there's only one assignment for this week, and this equation and this equation are part of it, but there are 3 more questions to that, which I will discuss on the next lesson for this week. So this is my second reminder. Go fill out attendance. And I will see you when I see you later in the week, okay?